Okay, good morning to all of you. In this class, we are going to discuss about representation or expression of gradient, divergence, curl, and Laplacian operator in Cartesian coordinate system by using OCCS. Before we have to discuss how to represent or what is the expression of gradient, divergence, curl and Laplacian operator in Cartesian coordinate system by using OCCS. First we are going to discuss in short about OCCS, orthogonal curvilinear coordinate system, because it is very essential to discuss this one, representation of gradient, divergence, curl, Laplacian in Cartesian coordinate by using OCCS, representation of gradient, divergence, curl, Laplacian operator in spherical polar coordinate system by using OCCS. Likewise, these physical parameters or operators, gradient, divergence, curl and Laplacian operator in cylindrical coordinate system by using OCCS. So it is very important that we have to clearly understand what is called the orthogonal curvilinear coordinate system. In this class we are going to discuss shortly. Okay, so as we have been discussed previously that the orthogonal curvilinear coordinate system is that coordinate system in which Cartesian coordinate system and curvilinear coordinate system are always coupled together. So here curvilinear coordinate system is nothing but either spherical or cylindrical. So OCCS is nothing but Cartesian coordinate system and spherical or cylindrical always coupled together. Okay, here you can see, if we are going to consider any point in the space P, so this point P is the intersection of three curves. Either we have to consider Cartesian coordinate system, also this point will be the representation of intersection of three curves. Spherical polar coordinate also same, cylindrical coordinate system also same. That means three curves are going to be intersect with each other at a particular point. I am going to show you. Watch carefully. See, here three curves are there, U, V and omega. Here two curves I can put like this. This is one curve. Here you can see, this is one curve, this is one curve, this is one curve and this is another curve. Okay, this is another curve like this. Three curves mutually perpendicular. Actually not three curves, the tangents are this one is the tangent to this U curve, this one is the tangent. Actually you have just considered that this tangent will be here. Okay, this tangent will be here and this tangent will be here. So these three tangents are perpendicular with each other whenever they are drawn from this point P. So as these tangents are perpendicular with each other, obviously the unit vectors along these tangents, so E1 cap along this tangent, E3 cap this one along this tangent, E2 cap along this tangent are also perpendicular with each other. So hence it is called as the orthogonal curvilinear coordinate system. As we have been discussed many times that either we have to consider Cartesian coordinate system, spherical polar coordinate system, cylindrical coordinate system. Any point in this coordinate system is representation of intersection of at least three curves. So here you can see this U, this is your omega and this is your V. Same figure I am going to do draw here to explain. You just watch. So these are the three curves which are intersects at the point P, this one, and this is the tangent for U curve, this is the tangent for V curve, this is the tangent for W curve. Corresponding unit vectors are E1 cap, E2 cap and E3 cap. So this is drawn in plain paper. So actual 3D view is like this. Carefully you have to watch. For U curve, this one is the tangent and corresponding unit vector is your U1 cap. For the V curve, this one will the tangent, corresponding unit vector is your E2 cap, and this is the tangent. This is the tangent for this curve, W curve, and corresponding unit vector along this is your E3 cap. Okay. Now, as we have been discussed previously that these three curves belongs to any one of the coordinate system, maybe Cartesian, maybe spherical polar coordinate system, maybe cylindrical coordinate system. So first we have to discuss if these curves are belongs to Cartesian coordinate system, then how it will be look like. Okay. So in case of Cartesian coordinate system, these curves will be the straight lines, right? So if this U curve will be the straight line, then this will be like this. This will be the U curve. Okay. We along x-axis, or we can say parallel to x-axis. Starts from this point and parallel to x-axis. If this V curve will be a straight line, then see, line also called as a curve. So if V curve is a straight line, it will like this along y-axis, right? And if W curve, this one will be a straight line, then along z-axis, this one, right? Perpendicular to both x-axis and y-axis. This one will be called as your W, right? So if it is so, here you can see that these three curves intersects at a particular point P, at point P, and the tangent to these curves itself, these curves. Okay, so if I am going to draw the tangent for this line itself, this line, so tangent for this line itself, this line, tangent for this line itself, that line. Okay, so if I am going to draw the tangent to these curves, so that is nothing but itself these lines. So the unit vectors you can see along this x-axis will be what? See, for orthogonal curvilinear coordinate system, for OCCS, for U curve E1 cap, for V curve E2 cap, for W E3 cap, like that. But now if we are going to consider Cartesian coordinate system, these three curves are along x-axis, y-axis and z-axis. So for this curve, that means for U curve in Cartesian coordinate system, what will the unit vector? Unit vector will be I cap, because this curve is along x-axis, or we can consider this curve itself the x-axis, right? So this curve itself the y-axis. So along this curve, what will be the unit vector? J cap. Along this curve, this one, what will be the unit vector? Instead of E3 cap, we have to write this one. So instead E3 cap, we have to write what? K cap, because this curve is along z axis. Okay, so this is all about Cartesian coordinate system. Now if we are going to consider these curves are belongs to spherical polar coordinate system, then what are the curves and what are the unit vectors? So here you can say that if I am going to consider this is the reference point, so what will the position vector of this point? So the position vector of this point in Cartesian coordinate system will be how much? R equal to we know this one, R will be equal to I cap x plus j cap y plus k cap z, right? So here one thing we have been concluded that even if Cartesian coordinate system also a point is represented by intersection of three curves. Here one curve, this is another curve, and this is another curve. Okay, now we are going to discuss about spherical yes, spherical polar coordinate system. Carefully you have to watch. This is the spherical, or this is the sphere, and here this sphere is there. This is the sphere, and in the spherical polar coordinate system, this is one point. Okay, this is one point P, and this is the representation of this point is the representation of uh, intersection of three curves in the spherical polar coordinate also. How it is? Carefully watch. This point is supposed here. Okay, this point is supposed here, point P, right? Now this sphere can be defined by variation of angle this way. Okay, variation of angle this way. Okay, and distance from the center of the sphere to outside. Okay, so here three curves you can found. One curve is like this, the so-called azimuthal angle, which represents the azimuthal angle. Another curve is like this. Another curve is like this, the variation of angle theta. And another curve is the straight line, which starts from this point, that means from the center of the sphere, and passed through this point P, and starts from the center. Okay, another curve is this one, the variation of angle phi, that is your azimuthal angle. Another curve is this way in spherical polar coordinate system, that is your variation of angle theta. So here three curves. One curve is this way, 2 pi angle, variation of azimuthal angle phi, and another curve is this way, pi, due to the variation of angle theta. And another curve is, this is the straight line passed through this point P, this point. Okay, this point P starts from the center of this sphere. So here you can see that three curves. One is this one, another is this one, and another this straight line intersects at this particular point. And if I am going to draw the tangents, here you can see, if I am going to draw the tangent for this curve, this phi curve will be like this, yes or no? Will be like this. If I draw the tangent for this theta curve, that means variation of angle theta, this curve will be like this, that means tangent to this curve is like this. So this point is the intersection of tangents to the three curves. Okay, for the phi curve this is the tangent, for the theta curve this is the tangent, and this is itself the tangent, and this is the line itself intersects at the point. So here we concluded that in case of spherical polar coordinate system, also three curves, this one, and this one, radial, this is the radial component, I can say this is the radial component passed through the point, starts from the center of this sphere, and this is the one tangent for the phi, or you can say corresponding u, and this is the curve corresponds to v. Okay, and this is the tangent for that curve, and these three tangents, or you can say the unit vectors for this one and this one and this one curves, are orthogonal or perpendicular with each other. So only for that, this is also called as your orthogonal curvilinear coordinate system. Okay, Likewise, we can define the unit vectors for this curve. See, this curve is belongs to phi. So for this curve, the unit vector will be how much? What the named as E phi cap, right? And this is the unit vector. This is the unit vector for theta curve. So for this curve, the unit vector will be named as E theta cap, right? E theta cap, okay? E theta cap for variation of theta, that means for this curve, or tangent, for the tangent unit vector for this tangent, okay? Now unit vector for this tangent, that means radial component, will be named as your what? Er cap, because it is radial radial vector or radial curve, and corresponding unit vector named as er cap. For theta variation curve, unit vector E theta cap. For phi variation curve, named as E phi cap. So you just remember these things. It will be required whenever we are going to discuss the representation or expression of gradient divergence curve in spherical polar coordinate system, okay, by using OCCS. Now we are going to go for the cylindrical coordinate system, and we have to check that how in case of cylindrical coordinate system also the tangents are normal with each other. So here one thing I am going to share to you. See, this is the sphere having the radius, suppose r, this much is the radius. If I am going to change the radius, so sphere will be larger, but this will be the curve, and this this will be the one curve, this curve, radial curve, and this will be the theta curve and corresponding tangent, and this will be the tangent to the phi curve. Either I will consider larger radius or smaller radius, then any point on the surface of the spherical polar coordinate system represented by intersection of three curves. So in this case, for the spherical polar coordinate, phi, theta, and this r, okay? Now we are going to go for the cylindrical one. Here you can consider this is a cylinder one, okay? This is the cylinder, this is the height of the cylinder, and this is the surface of the cylinder. So now consider this point P at anywhere on the surface. So here suppose this point P, I am going to show you, wait, and this is at the center, and this is the point P, belongs to point P. That means suppose we are going to consider this point is at here, okay, in here, right? Now how I am going to locate this point? How I am going to locate this point on this surface of this cylinder? On the surface of this cylinder, how I am going to locate? What are the variations? Here you can see one variation is radial component. That means what is the distance from the center to this point? What is the distance? This is the radial component one, okay? Not for the center, but from the axis. From the axis, what is the distance of this point? See, here you can see that from this point to this point will be same distance if I am going to consider from here to here also, okay? You just consider this is a perfect cylinder. It is not exactly perfect cylinder. You just consider this is the perfect cylinder. So here you can see that one parameter we need, what is the distance from this axis, one parameter, or we can consider one curve itself. This is one curve which is passed through this, and from this axis to this point, what will be the distance? So one parameter, okay, this is the distance, one parameter, and it is represented by this curve. That means if this radius will be changed, that means cylinder r will be changed. That means cylinder will like this, it will be increased size. Okay. Another one, if this point will be change its position on the surface, that means this angle is changes, right? This angle, one angle, this one, this surface, this one, okay, this one, and suppose this one is your changes means like this, okay. So this angle, suppose this curve named as theta. If theta changes from 0 to 2 pi, that means this point moves on this surface of the cylinder from here to here. From here to one round, it will move one round on this surface of the cylinder. So another parameter or curve we need to represent this point is your theta, or this curve is your belongs to change of theta, okay. And another parameter it will be required, that how much height from the base this point is, how much height, okay. So here this is one curve, theta curve, this is the radial curve, another is your height, one height measurement we need, this is the curve, this is the another curve we need, okay. This is the another curve we need. That means here you can see that for this point we need three curves. This is one curve, that means how much distance from this axis this point will be. This is the radial component, another is the theta component, and another is the height component or height curve, right? So here consider this one is belongs to u, and this one is belongs to let's consider this one, this r is your u curve, and this is your v, and this is your w, right? So instead of u curve, this r curve we are going to consider. That means for cylindrical coordinate system, instead of u we have to consider r curve. That means instead of u cap or belongs to u curve, this will be e1 cap. Instead of e1 cap we have to consider what, er cap will be the unit vector, and this is the theta curve. So instead of v we have to consider e theta cap. For the v curve, this will be this one, change of theta, so belongs to theta, e theta cap, and for the w curve this will be e z cap. So for this curve er cap is the unit vector, for this curve e theta cap, for this curve height curve will be e z cap. And here you can see that these three unit vectors are normal with each other, okay. Here you can see easily, this is one unit vector, this is another unit vector, wait, this is one unit vector for theta curve, this is the radial curve, and this is the height curve. So here this is the tangent to the theta curve, and these two curves are straight line. So these two curves tangent itself the straight line. So here you can see at this point P, these three unit vectors are normal or orthonormal with each other. So hence this will also belongs to OCCS or cylindrical coordinate system, also belongs to orthogonal curvilinear coordinate system, right? Okay. So for cylindrical coordinate system, we have to consider, instead of u we have to consider uh, r curve, and corresponding unit vector will be er cap. Instead of v we have to consider theta curve belongs and corresponding unit vector will be e theta cap, and instead of w we have to consider z and corresponding unit vector will be e z cap. Likewise, in case of spherical polar coordinate system, as we discussed, instead of u we have to consider r and corresponding unit vector will be er cap. Instead of v we have to consider theta, e theta cap. W, this will be phi and corresponding unit vector will be e phi cap in case of spherical polar coordinate system. And in case of Cartesian coordinate system, I cap, j cap, k cap, instead of e1 cap, e2 cap, e3 cap, or corresponding u, v and w cos. So in short, we have been discussed about Cartesian, spherical and cylindrical coordinate system, how it is directly related with OCCS, orthogonal curvilinear coordinate system. So in our next class we are going to discuss representation of gradients, divergence, curl and Laplacian in Cartesian coordinate system by using OCCS. As we have been discussed in this class that u is belongs to x, corresponding unit vector will be u, corresponding unit vectors will be I cap, j cap, k cap, correspond to v, correspond to w. Okay, so likewise, in case of spherical polar coordinate system, whenever we are going to discuss, the u will be r, v will be theta, and w will be phi, and corresponding unit vectors will be considered as e1, sorry, er cap, e theta cap, e phi cap. Likewise, whenever we are going to discuss about cylindrical coordinate system, expression of gradient, divergence, curl, Laplacian in cylindrical coordinate system by using OCCS, at that time u will be r, v will be theta, w will be z, and corresponding unit vectors are er cap, e theta cap, and ez cap. So here we have to stop our discussion for this class. In our next class we are going to discuss representation or expression of gradient, divergence, curl and Laplacian operator in Cartesian coordinate system, then spherical, then cylindrical. Thank you so much for watching this video. Thank you.